Each time we do capacitors, every year I get the same questions. Miss, how do we go from this graph, we're charging a capacitor with time, a nice smooth curve coming down to the axis. Of course, in discharging, our graph is given a specific equation. So in our first instance, we have discharging, and then we have the second instance, we have a charging graph. No problem. But the true question that we normally get is how does the equation go from Vc is equal to V0 e to the negative t over Rc to this. Vc is equal to, sorry, V0 or Vs supply voltage multiplied by 1 minus e to the negative t over Rc. And of course, there's a big question mark. Today's video, we're going to explain the mathematics behind how we get from one capacitor graph for our discharging formula to a charging formula. Has everything to do with mathematics. So I'm going to go through that right now. First things first, let's start with the base. And our first graph is a graph of the equation. Let's write it in y equals e to the x. It tells us it's going to cut our y-axis, sorry, at this value of 1. So it means, therefore, that the shape of our graph has a y-intercept, sorry, at 1. Our amplitude here is understood as 1. Alright, so it cuts the y-axis at this point, and of course this point is given as 0, 1. Now, how do we get from y is equal to e to the 1, which is our amplitude as we said, e to the x? No? Well, let's check. If we reflect this graph on the y-axis, meaning that it will now look something like this. So let's see. I will get the graph in this shape, of course, coming down like this. I wouldn't let it touch the x-axis as yet, but we get an equation that looks all too familiar. So I'm going to redraw it right here. This is the equation that we are looking at. So when we reflect y equals e to the x on our mirror line, which is now our y-axis, we get this graph. If that's the case, it's still going to cut at 1. Our equation, and of course the segment of the graph that we are actually looking at is this section here. Our equation now becomes y equals e to the negative x. It's an exponential decay curve, also used in atomic physics, quite loosely. Now you might recognize this graph quite easily. This is therefore our graph for our discharging our capacitor. So this is our discharging graph for capacitance. So discharging means this is our capacitance voltage, our maximum voltage at V is equal to 0. So what is the equation of this graph? Let's follow suit. Our y-axis, it's Vc, equals our amplitude. It's understood here as 1. In this case, our amplitude is V0. E to the negative. Instead of x, there's no x-axis, we have a time axis. So it's t, but we have a constant involved, 1 over Rc. Alright, now this was explained before, but this is where we get our first graph, our discharging graph. And that's all well and fine. Let's clear this up a bit and see where we move from here. So this is fine. Moving, however, towards a charging of a capacitor graph where we have voltage across the capacitor versus time, well, that's where the question lies. If I take this graph, this equation, where it is now y is equal to 1, where it cuts the y-axis, that is, e to the negative x. And let's put a little note. What are we going to do with it? Let's reflect this graph, of course, on the x-axis. if we reflect that graph on the x-axis, now I'm just going to redraw that graph. First of all, it was actually here. This is our mirror line, so I'm going to just shade the back of it so you'll have a better idea. If we reflect that graph on the x-axis, well, what do we get? We get a graph that looks, now keep in mind this is cutting it at 1. We get a graph that cuts our y-axis at -1. Look at the shape of the graph. Does it look pretty much familiar? Yep, it does. What is the equation of this line? Now, this is what we are actually going to pay attention to. What is the equation? The equation of this line is y equals, it's reflected as an amplitude of -1, -1 e to the negative x, and write it as minus e to the negative. It still doesn't give us the equation. It's not charging our capacitor graph. What we need is a graph above the x-axis. So let's take it up a notch one last time. If first of all we want this graph to pass through the origin, of course, which is of course this point here, what do? Well, we shift that graph 1 by a value of 1. We move that graph by a value of y plus 1. So we add 1, y plus 1, of course, to our graph. What is going to happen? Therefore, the graph is shifted upwards. Our graph now looks like this. Okay. Our graph now looks like this. Does it look familiar now? Y equals to minus e to the negative x. That's our original equation from right here. Plus 1. We will therefore write it as is y equals 1 minus e to the negative x. Does it look familiar? Well, let's check. How does this relate to our capacitor graph? Our capacitor graph, therefore, with everything, of course, being above the x-axis, now follows suit. We have our VC axis, our time axis. Graph is now drawn like that. So we get our y-axis is VC. It's equal to, well, we have an amplitude of V0 right here. So I'm going to write that in. Our amplitude is included in the equation of our graph. Multiply by 1 minus e to the negative t over RC. And there we have it. Those are our graphs that we use. Didn't come from thin air, it actually comes from a little bit of mathematics. Alright, thank you, and teach someone what you know.